Did you repress record?
Yes.
Okay. All right. Next step, we have gotten our intrinsics from our lens calibration. We've now solved for our extrinsics, and we've solved for those extrinsics for every frame in the case of a UAV. So now we have, to use Brittany's baking analogy, our ingredients, and now we need to put them together into the camera projection matrix recipe to actually make our rectified or projected final image. And this is basically this final step in the process that allows us to make the really beautiful maps of cool sandbar morphology or whatever you want to make maps of from just taking the images of the coast. All right, so outline. We're going to talk about the design array, and then we're going to walk through how to do this for a single camera. All right, the goal of what we're trying to do is go from oblique view to a rectified, mapped, or projected, or orthophoto. Those all effectively mean the same thing. You're going to see them called different things in different literature, but they're effectively all words for doing the same thing. As we talked about a little bit before, the intuitive approach might be to do a forward model where you start with your UV pixel coordinates and you go forward and find the XY location of every pixel in your image. However, that's not sort of the easiest approach to use. You can use the toolbox to go this forward direction, but you need to have some additional pieces of known information that we may not actually have. So instead, we go the opposite direction that we taught you this morning. So that is starting with an XYZ list of points that you are interested in. Typically, that is the grid of the final image that you want to project onto. And then we use that camera projection matrix to go backwards to find the UV pixel locations, then apply the distortion to get to our distorted UV pixel locations, create a lookup table where we can extract the RGB values for those XYZ points. So this is the image we've been showing you a bunch of times. The yellow grid is sort of what we call your target world grid. So you define a grid where you want your image to be. You're probably going to define a grid that's not exactly the same size as your original image. So it might be a portion of your image, or it might extend off of your image field of view, which would sort of be the case that's illustrated in this example. A few things to remember is we do need to know the Z elevation of our grid to make this work. For water pixels, we typically use the Z elevation of the tide. We do not try to account for waves going up and down. We just give it a flat Z tide elevation. And then best practice would be to find a digital elevation model of your stretch of coast and go extract rough Z elevations for your beach and dune. You don't have to do that. You can just assign if you're mostly interested in oceanographic processes, you can just assign a constant Z value to your whole image that's equivalent to the tide. If you are trying to track shoreline position, this gets a little tricky because the shoreline with tide can move up and down the beach. So if you're telling this series of equations, the frames through, or the images through time, that the shoreline is always at the same elevation, when we know it's not, it's going up and down the beach, that can introduce errors as well. The higher your camera is looking at the shoreline, the closer your shoreline is to the camera, the smaller those errors will be. The farther away your shoreline is and the lower your camera is, the larger impact the unknown elevation of the shoreline will have on your final feature or your final measurements of shoreline change, for example. All right, so we're basically mapping our points in the world to corresponding pixel points, getting the RGB intensities, and then putting them back onto our grid. Why am I stuck in a loop? All right, there we go. Oh my goodness, what is going on? Okay, I see. The bullet points are changing. All right, I got you now. So lots of points, like I mentioned before, may not actually lie in the image. So those are determined by a flag in the distort UV and an XYZ to distort UV. So that'll tell you which of your grid points are not actually in your image. And so this is giving you the sequence of the functions that you can call. You use XYZ to distort, and then you can use UV distort to get the actual distorted image pixel locations. Word. Okay. All right. So we talked a little bit about this. You've seen this graphic before. We were previously talking about it and making sure that we measured our coordinates or our GCPs in the correct coordinate system. And the world coordinates that you put into your camera projection matrix need to be in that exact same coordinate system. So again, it can be geographical or it can be local. And the coordinates you are inputting are basically the grid locations over here at the resolution that you want your final image to be projected at. So if you want your final image to have a 5 meter resolution everywhere, then you should create a 5 meter by 5 meter grid. If you want your final image to have a 1 meter resolution everywhere, you create a 1 meter by 1 meter grid. Now, that may be super over resolving things at far range, but if, for example, you're only interested in some small portion of the shoreline, maybe there's some interesting beach cusps that you really want to look at, you could even do a 50 centimeter grid just for that small little portion that you're really interested in. So you don't have to input a grid that's the whole size of your image. It depends on what you're most interested in. All right, so this grid generation happens in D, grid generation, as it's aptly named in the toolbox. And as it says here, you have to have completed A naught, A, B, and C. And then you need to make sure your core functions are on the active path. All right, so the inputs in D grid generation are your extrinsics and intrinsics from C. You need an image to rectify. You need your target grid resolution and your target grid extents. So that's where we were talking about how big of a grid do you want to input and what resolution. And then you need to have your grid elevations. What you get out is a map file with your both your grid in your local coordinate system and world coordinate system, if you've defined that, and some example PNGs of the rectification of the image. And just a reminder that you need to estimate the elevation of your water level. Typically you go grab that from a nearby tide gauge. If you want to create a spatially varying elevation file that includes the dune elevations and average beach topography, you can do something like that, but you have to do that sort of outside the toolbox, and then the toolbox will ingest that. So if you are running a fixed camera station somewhere and your tide's going up and down, you might want to have an additional script that's creating a DEM to feed into this every hour, that's updating those Z elevations based on the tide change. And then your grid is what goes into your vector over there, the X, Y, Z, 1. That typically is going to be a 4 by however many points in your grid vector that you're multiplying to make all the matrix dimensions work out. So you don't have to just do one point at a time and loop through. the beauty of matrix multiplication is you can make that variable a 4 by n number of points in your grid and do it in one matrix multiplication step. I think this is on to you, Brittany.
Okay.
Because I think the rest of this is just walking through the script.
Yes. So we will start going through D. So I'm going to skip the PowerPoint and then we can come back later, but I'll just kind of think PowerPoint's just more for notes. So I think that's Kate's done with her lecture. So there for Kate. So yes, so so D is to kind of explore your imagery. So make a grid that you're going to use for all of your future products. And so we'll kind of go in here. So this is actually probably one of the scripts you can play with the most. So we're going to go into our input and saving information. Again, I'm just going to ask you guys to add a 2 onto the O name. And then also the G name, add a 2. That way we can play around however we want and we won't mess up the future stuff. So I will say there is, and I'll show you guys later, there is a flag in one of our functions. It's called teaching mode. And so teaching mode is actually going to bring up all these figures and show like where your grid looks like in space and things like that. If you were doing this operationally, you'd probably set that to 0. But we're going to keep it 1 because we're teaching. And so again, we're just going to give it an image. You could pick any image you want since we calibrated our camera. For UAS, it's going to again be the first one and the first one. So you want to do your initial data solution and your first image. And so here we have that, an image path, an IO-EO path. Again, this is kind of the same information, what our coordinate system is just for our records. And so this is the coordinate system, the local coordinate system where we want to define this. Now, we have this is assuming that your original input of your GCPs and your extrinsics are in a projected geographical coordinate system. We did it this way because a lot of people go out and collect and they don't necessarily know what they want their local coordinate system to be, or it's kind of hard to guess at first. And so rather than if you guessed wrong and having to do your extrinsics all over again, we're going to start with world and then define our local here. If you did happen to do local already, we do have the option where you just set these all to 0. But in this version, we didn't. So the local origin that I put here is an easting and northing, and then the angle, as Kate showed in that diagram. This is what we use at the FRF. It's a known coordinate system. You know, a lot of times for UAS, if you don't have a fixed coordinate system, you just want to see what it looks like. Sometimes I'll just take where the extrinsics, I'll just take where the UAS actually is, and then just kind of make it relative to that. You can do it different ways, but mostly you always want it for things to use in a lot of things like CBATHY and VBAR. You always want your X positive offshore. And so with this, we can play with it and we'll be able to change it and see how we get that. Because with duck, I'll be honest, it's super easy because we're almost north. But when you start getting on West Coast beaches, that's when we run into confusion, a lot of issues. We have this local input flag. So when we define the extents of our grid, we can do it in absolute coordinates or we can do it in local coordinates. So what I typically like to do, and I find a lot of people do, is let's say we did make it our UAS location. I'll say I want 100 meters to the north and 100 meters to the south, or to my left and to my right. And that kind of bounds my area of interest. It's easier to put that rather than doing the math and finding the coordinates. But you can do it that way. But I just like doing it this way. So we have the local flag input is 1. This is our limits of our grid, and this is our resolution, all in the same meters or units that we're doing our toolbox in, that our extrinsics are in. This is our elevation, what Kate was saying. And so for this one, it's not, since we're at Duck and, you know, our elevation is pretty close to mean sea level, like our tidal elevation, what we're rectifying, it isn't that big of an issue. However, like when we go to the Great Lakes and like the mean tide is 0, but we're 60 meters high, we have to make sure that the elevation is relative. They're all in the same coordinate system. So like, that's where we have to kind of be careful there. But for this little exercise, we can keep it at 0. So this right here is all for the multi-camera stuff. So we'll go ahead and skip that. So if we just go ahead and run it. So this is what teaching mode gives us. So it gives us an example grid of what it looks like in local coordinates as well as geographical coordinates. So here's our geographical coordinates. And then we actually plot our grid back onto the image so we can kind of see the pixel resolution that we're pulling. Now from here, this is really difficult to see because we have a lot of points. So we'll go back and play with it a little bit. But you can see right here, this is the difference between the geographical and the local, where we have it perfectly cross-shore aligned with the pier. So if we go back, one thing that we can easily get change is, let's change our resolution. So let's change it to 20 and rerun it. So you can see now our grid that we define is much more sparse, so our XYZ grid, and as a result, our points are much more sparse. But you can also kind of just see how this actually works when we're pulling images, because you can see each pixel represents a larger amount of space the further away you get from the camera. Because you can see, like, so this is 20 meters, and then all the way back here, the difference is between 20 meters. So your pixel is doing a lot more work offshore. And so this kind of just helps you visualize that and see where you're getting good resolution. Yep.
When you go from the physical XY to the distorted U to V, I presume you're not at a precise, like, integer pixel.
No, you're not. Well, so that's one reason why we go from XYZ to UV, because we do, like Kate said, it's a lookup table, but it's actually, we just use a MATLAB interp function. But that makes a good point, though, because when you go from UVD, like if you start from UVD, this guy, to go to XYZ, like that's where things kind of explode, because it can be a range of values. And so that's one reason we don't like to go that way.
You experimented at all with like an automated way to determine your frame size?
I usually, with UAS, and GUI Bathy does this, I usually take my first extrinsic and I go 500 meters out and like 250 on either side, kind of depending. And that will like at least give me a good starting point. Then I start to rotate and to play with it until I get it how I want. But that's kind of where I start with it. And then I'm trying to think. So, but again, we can change the rotation. So let's say we change 60. And so now our local coordinate system is not oriented right. You know, our geographical one, it changes a little bit. It's still in the right spot in space, but because I defined it in locals, that's why it's changed a little bit. But, and then let's see, so I'm going to take the cross shore and I'm going to cut it down by a lot and go to 100. And then I'm going to change this to like 20 centimeters and we'll see if this breaks. This may break something. So just, this is a really fast computer. So if it takes a while, I probably wouldn't try it on yours. Yeah, I didn't like that. Oops. Okay. That was a mistake. There we go. So let's try this. Let's do 100 there, 100 and 100. Okay. So now you can see like we have really, oh, it's trying to do my 1001 still. It's nice and resolved and it's really good resolution right there, but it's, yeah, close. Hi. Okay. Yeah, now I broke it. But anyway, it was working. Yeah, so that's, this is just a good way to play with how, playing with resolution changes something. Now, just as a quick demo to show the actual effect that elevation does have when you're rectifying and having the correct elevation. So this was assuming that we were at 0. Now, normally you probably wouldn't be this off, but let's say our sea level was actually at 10 meters, or it was at the elevation almost of the pier. I'm not sure if this will be this isn't even a big enough change, but it does, if you were to do a difference, it does change it quite a bit. So let's make it, let me see, try to make it 50. So yeah, so it changes things. So we want to just be cognizant of that. Usually it's generally 1 to 3 meters, but yeah.
Brittany, one thing I wanted to add is you mentioned rectifying to the tide level is what you want to do. Technically, you mean the measured tide level.
Yes.
Lucky here at the upper end, you know, an ice gauge, most like, no, and so then you need to think about having instrumentation in the water to measure the water level and also doing a tidal analysis.
Yep. Yeah, if you have a big tidal range, it's really important. You know, for our stuff, we usually use NOAA predictions. We use, if there is a measured, we use measured. You know, and I think kind of more of an advanced class we can get into, particularly if you're looking at run up, if your camera's close to the ground and you have a very steep elevation, it's actually really important to have a good idea of your DEM to rectify it to the actual slope of the beach. You know, for kind of big picture stuff like we're doing, you know, it's okay to assume the tide, but for low, super low cameras and for people really particular and like precise run-up values, it's important to have the actual, you're going to actually project onto your beach DEM. All right, so I think we'll take a break. We're at break time, right? Mm-hmm. Okay, sorry guys. So we will take a break and then we will move on to image products.